first, I just want to look at the course, look at what we got coming up. Just as a reminder, we got 3 weeks left of this semester, all right? And that's it, okay? I'm happy some of you guys who are missing work got some of that work turned in over the break and over the weekend, and I very much appreciate that. And your grades have improved if you've done that. If you have not, there's still time. You can get stuff done. So here we are. This is the course. This is the student view. This is close to what you guys should be able to see. I'm going to look at the calendar first. I believe I've updated this. Yes, I have. All right. So calendar here. Here's the month of December. Right now we're on December 2nd. All right. I've filled in as much of this as I could for the next 2 weeks. Everything for this week, except for the self-assessment, has been published and it's ready. We even had one student try to do the discussion board already. Anyway, so there's this week, there's next week, and then there's finals week. Good morning, Destiny. All right, this week we will have kind of our regularly scheduled stuff. We've got our live class. We're going to be introducing exponential decay. All right, so this is just the opposite direction of what we've been doing. We've been doing exponential growth where the our functions are increasing. Decay is just decreasing. All right, so we're going to be going the opposite way. We'll have our live class resources. As usual, those will be updated by the end of the day. We'll have a discussion board for after class. I'll go over the discussion board after our lesson today because it'll make more sense after the lesson. Then on Friday, again, we'll have another discussion board. I will make the Unit 5 self-assessment, which is the last self-assessment we'll have, available this week. You may or may not be able to complete it this week, but you have through the end of the semester to complete that. I wanted to give plenty of time to work on it and make it available early so that you'd have time. Right? The absolute last day that I can accept work is December 18th. Right? The last day of school. By the end of that day, if it's not been turned in, it's not going to be included in your grade. All right? That goes for all the assignments. So that's the only reason this is available. It is not, you don't need to do it that day. You don't need to do it this week. You don't even have to do it next week if you don't want to. You can do it the week of finals. However, I wanted to make it available. Next week, there will be one more discussion board, and then that's it. And that will be this discussion board will be the last assignment semester. Okay? So, over the next 3 weeks, right, this week, next week, and finals week, there will only be 4 more assignments in the class. Okay? 3 discussion boards and the self-assessment. There will be no more CYU assignments assigned. This is everything. Our day of the final, this being second period, will be the 16th. I've got the final schedule here in blue. All right. You have your finals for period 1 and 2 on the 16th, Wednesday the 16th. All right. So you'll see me from 10:50 to 12:50. It's a 2-hour block. We do not have an actual final. The day of the final will be used for you to get work turned in. Anything you haven't turned in, anything you want to turn in. The bare minimum to be excused or be checked out of the class is to have the 3 self-assessments turned in. All right. If you have not turned those in, that's what you will be doing the day of the final while you're logged in the Teams. All right, so I can verify that they've been submitted and then release you from the class once they've been submitted. Okay. So that's the whole point of the day of the final is to come in, check in. If you have not submitted all of your self-assessments, the 3 of those, then you will stay in the class, work on that on your own while I'm obviously logged into the Teams as well. So if you have questions, you can ask for help. It can be supported while you get work turned in. Beyond the 3 self-assessments, if anything else you want to turn in, you can work on the day of the final. So you could use that 2-hour block while you're logged in to turn in discussion boards, turn in check your understanding assignments, anything else that you want to submit to improve your grade should be done that day. You will have through the last day of school, right, December 18th, to submit assignments. So if the 2-hour block on the day of the final on Wednesday is not enough time, that's fine. You have the rest of the week to still turn stuff in, okay? Any questions about the last 3 weeks or the day of the final? So once again, on the day of the final, if you submitted all 3 of the self-assessments and you're happy with your grade, then essentially you'll come in, I'll mark you present, right? I'll make sure you're here, and then you'll be excused if you're happy. If you've submitted all 3 self-assessments and you're not happy with your grade and you'd like to make some changes, you can, resubmit a self-assessment. You can complete other assignments to improve your grade. If you are currently failing this class the day of the final and you have submitted assignments, you're going to have to do some work to bring your grade up. That's what I would suggest. You can turn in some extra assignments to do that, right? But that's what the day of the final will be. Basically trying to make sure that everyone can pass if at all possible. Okay? Any questions? All right. So again, this is what the last 3 weeks will look like. The self-assessment hasn't been published yet, so if you click on it, it's not going to work. It's just going to say that that isn't available yet. But everything else this week should be working. All right. So I'm going to show you guys that first before we get started. But yeah, now we're going to get this thing going. And one other thing, we'll just take a look at our module for this week. All right. It's the same basic module we've had. The self-assessment doesn't show up yet because I haven't published it yet. So here's that. Just as it normally looks. I do have videos for exponential functions already because I made them last year. So if you want to see examples of how to do exponential functions, we have growth and decay. All right. These are available. They're already published and ready to rock and roll. So those are there. Don't forget about those if you need to look at some other examples. Yep. So there's that. So now, I want to talk about first, when I was grading stuff over this last week, many of you guys kind of misunderstood the question on the quiz having to do with the compound interest. If you haven't done this yet, this should help. If you have, you can go back in and make corrections and resubmit if you like. So on our quiz, we were presented with 2 options, right? We had option 1, right, which was essentially you deposit, $100 in a savings account. right? And then add 100 every month. Then we add option 2, which is take that same $100, right? But this savings account earns, I think we said 3% interest. That is compounded monthly, right? And I asked, essentially, which one will have more money in 20 years, right? Right? This was the question, essentially. And you had to choose option 1 or option 2, and then explain why one was better than the other. First thing to point out, option 1 is linear. Option 2 is exponential. Okay. Option 1 has the rule y equals 100 plus 100 times x. Right? Whereas x, right, this represents the number of months. Option 2 will have the rule 100 times 1.03 to the x, where again, the x represents the number of months. Now this is where many of you guys made an error when using this function. If you found this function for option 2 and for option 1, is that you used the number of years instead of the number of months for the value of x. Right? Whereas if you only do 20 times of this, you will find that option 1 is the better option, because over, essentially a little less than 2 years, yes, option 1 will have more money, because 20 months, right, it's a little bit less than 2 years, but we need 20 years of time. All right, how many months are in 20 years? Right? Can someone tell me, how many months are in 20 years? Yes, Nicholas, 240. All right, so we're calculating for 240 months. So that means for option 1, right, in 20 years, right, we have 100 plus 100 times 240, which is 24,100. right? It's not bad. Not a, you know, any amount of money to scoff at. However, when we do this to option 2, we have 100 times 1.03 to the 240th power. Now that is a larger number. That we end up with 120,485.26. All right. So again, the major error that many of you made was that you only used 20. In a compound interest problem or population growth problem or any exponential problem, you need to be mindful and very careful about what is the unit of time or what is the unit of, like I would say, iterations being used. Are we talking about minutes? Are we talking about hours? Are we talking about days? Right? Depending on what unit is being used, right? In this case, we're doing months, right? So we have to count the number of months that we need to calculate for. In this case, it's 240 months because we're talking about 20 years. Right? Sometimes problems will be like, hey, every 20 minutes this thing happens. You know, how many things do I have after 6 hours? Right? You need to multiply 6 by 3 because there's 3 20-minute time periods in 1 hour. So you have to make that next extra calculation. It's not always going to be, you know, using the values told as the value of x. Right? It's not like, hey, it says 6 hours, so 6 goes in for x. That's not the unit of time we're using. We're using 20-minute time periods as the unit. Or we're using months, or we're using, you know, quarter hours or something, right? You have to pay attention to the unit being used. Okay. Is there any questions? So again, if you did not do the CYU from the week before break, this should help. If you did do it and you didn't get the points you wanted, this will also help. You can resubmit and get more points. All right. So don't forget about that. I'll post these notes into Canvas just so they do all the notes we do in class. They'll be available later if you need to look back at them. All right. So now moving on to our next topic, we're going to be talking about exponential decay, right? And when something decays, it shrinks, it gets smaller, right? So we're talking about decreasing values. All right. So I want to start by just looking at this graph here. All right. So we're looking at this graph. Right? We've got a red line here. We've got our blue line or green, maybe, I don't know, over here. What type of function is this red line? Yes, all right, thank you. It is a linear. Right, this is a linear function. Yes, Destiny, thank you. Oh, no, Jocelyn. Oh, darn it. Sorry, Jocelyn, you're not able to see the screen. That sucks. You could try to like close out of Teams, like leave the meeting, close out of Teams, and join again. Sometimes that helps kind of kick the screen back in. All right, so then by process of elimination, this other line here, what type of function is this line? Yes, Eileen, exponential. And this is an exponential function. Both of these functions are decreasing, right? As we go from left to right, the value on y is going down. So they're both decreasing. All right. So as we go left to right on this graph, which one seems to be decreasing faster? The linear or the exponential function? Yeah, the linear one does, right? So exponential, it may have started decreasing faster, yes. No, that's okay. If we go up higher, it probably has a faster, a steeper decline than the linear one at first. So kind of like when we looked at the exponential growth functions, they start slow, right? And then they increase very fast as we go farther to the right, right? They start increasing faster. Exponential decay functions, right, where we're losing value, start decreasing fast and then slow down, right, as they move to the right. Okay. So let's look at an example. All right. So we're going to look at this example here. We have most popular American sports involve balls of some sort. In designing those balls, one of the most important factors is the bounciness or elasticity of the ball. For example, if a new tennis ball is dropped onto a hard surface, it should rebound to about 5/9 of its drop height. All right. So we're going to need that number. All right, let's work on these problems. We're going to look for patterns. We're going to be looking at tables, graphs, and rules again, as we have for all of our other functions. So suppose a new tennis ball drops downward from a height of 30 feet. In a paved parking lot and keeps bouncing up and down again and again. The rebound height of the ball should be, again, 5/9 of the drop height. Right, we have this table and graph area that we're going to use to show the expected heights of the first 10 bounces. All right. So we have these two numbers. Again, just like in our linear functions and our exponential growth functions, what are the two numbers we're always looking to identify when we're trying to use these types of functions? What are the two numbers we need? Always two numbers. Right. We have these two numbers. We need two numbers. What do we call those two numbers in our functions? Yes. So Eileen has the rate of change and the y-intercept. Yes. Those are the two numbers we need. All right. Jocelyn, yes. Y and x, yes-ish, right? We can kind of think of it as the y value we need is the y-intercept, and the x, right? If we're thinking of the change, we need that. but typically we use y and x as the placeholder for values we're finding or that we're replacing. So we have this height of 30 feet. Is that the rate of change or the y-intercept slash start value? All right. Good guess, Destiny. Our rate of change is actually the 5/9. Right? Yes, the 30 feet is going to be our y-intercept, the start value. Okay? And so now we already know what the basic exponential function rule looks like. If we remember, they have the form y equals a times b to the x. All right? A, the start value, b is the rate of change. All right? And then we can kind of think of x as unit of time, right? In this case, our unit of time is bounces. We're just counting the number of bounces, right? Okay, so when we are at 0, no bounces, what's the height of the ball? The ball has not bounced yet. Again, good guess, Destiny. So again, the 5/9, right? That is our rate of change. So that's what we're going to be multiplying by. That's what's going to go in for B in our rule, right? What is the height when we start before we've dropped the ball? Right. So our starting height, again, based on the y-intercept start value that we've identified, is 30. So when we're at bounce 0, nothing has happened yet. We're at our start point. We have a height of 30 feet on the tennis ball. Once it's bounced one time and we drop it, it hits the ground, it goes up. It's going to rebound to a height of 5/9 of its drop height. All right. So we take this 30, right, and we multiply times 5/9, and that will give us the next value. Right. And that gives us 16 2/3. let's say 16.67. Then we multiply by 5/9 again, because each bounce, so it goes up to a height of 16 2/3 feet, and then it falls again to the ground and bounces. It'll bounce up again to 5/9 of the height that it just came from. So we do times 5/9 again, and we get about 9.26. Okay, and we continue. We get 5.14. 2.86. 1.59. 0.88. 0.49. 10. We end up with this as our completed table here. So after 10 bounces, essentially the ball is on the ground. Now, there's other things at play here that we don't consider in this type of problem that we would only consider if you were taking a physics class, but we're not doing that and we're not going to worry about them. So, what questions do you have so far? All right. Now we're going to use this. We're going to graph. Let's see. 1, 2, 3, 4, 5. How would you do a number multiplied by 5/9 in the calculator? Oh, okay. So the best thing to do is in your calculator, depending on the calculator you're using, like if you're using Desmos, I'll show you how to do that. So if you're using Desmos and we're calculating this, we would do 30, right? And we can just do in parentheses 5 divided by 9, and then close. Oops. Really? Out. There. Right. So we can do it that way. If you're using like a regular calculator, there's a couple ways you can do it. It depends on your calculator. Let's see if I can get this to work here. Give me a second, guys. I'm going to try something. Yeah. Kind of ish. All right. So if you're on just like a regular calculator, right? Right. You can do, type in like 30, and then so on my calculator here I have parentheses. It depends on what calculator you have at home. You can just do open the parentheses and just type in the division. 5 divided by 9. close the parentheses, and that'll work as well. You get 16 2/3. If you're on your phone, right. If you're on your phone, like and you're using just the regular calculator, you're going to want to do it in steps. When you're multiplying by a fraction, you multiply the number you're multiplying with by the numerator and then divide by the denominator. So you do 30 times 5, an answer, divided by 9. So we get the same answer. And then you would continue by saying, okay, well then times 5 divided by 9, that's the next answer. So it's a few different ways that you can calculate it, depending on your calculator. Hopefully that helps. Where'd it go? There we go. You're welcome. All right. So where am I at here? Here we go. All right. We have our graph here. Go by 2s. 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and finally 30. Yeah. 1, 2, 3, 4, 5, 7, 8, 9, 10. It's okay that I'm not going to need all the graph here. And then we'll just plot our points. We're starting at 30. And then when we get to 1, we're at 16. And let's be right about here. All right, 2, we're at 9.26. About here. 3. So you can see that it starts like decreasing slower, right? Essentially, by the time we get to 10, we're basically on the x-axis. And again, we have our x-axis and our y-axis. And then we can try to connect our points as best as possible using a nice smooth curve. We'll see if I can do this today. Close enough. Okay, this is what the graph looks like. It makes sense for the situation. You know, when you drop a ball and you don't touch it again, it will eventually come to rest and be on the ground. That makes sense. So now, I'm not going to worry about question A here. We know that the rebound height changes from one bounce to the next because it only bounces up to 5/9 of the previous height. Right? And this is shown in the shape of the data. Right? The height decreases. We can see this in the shape, right? The curve, because the curve is decreasing and slowly goes to like 0. Right? Our now next rule. Right? So we have now, right, times our rate of change, 5/9 equals next. starting at 30. So again, we have our two numbers at play here. We have the rate of change, right? And the start value. Question C here, we want a rule, y equals 30 times 5/9 to the x. X represents the number of bounces. 30 again is the start value. 5/9 is our rate of change. All right. Any questions on how we got these rules? All right. So question D here. That a line is exponential only if it's curved. If you're only looking at the graph, that would be a clue that it's that it could be exponential. Unfortunately, there are other forms of graphs that curve like that. It's not, you can't be 100% sure that it's an exponential function. If you're given the choice of saying, hey, here's a graph, is this exponential or linear? And it's curved, we can say, okay, well, that's, given those choices, it's probably exponential. But there's other mathematical functions that can look like an exponential function as well. So we can't just make the blanket statement that that if we see a curved line like that, that it is exponential all the time. I know that's not a great answer, but until you've seen more types of functions, that's kind of the best I can give. As short an answer as I can give. So, sorry if that doesn't help. In this course, I'll always try to give you options that are reasonable. I won't ask you to identify something that's outside of what we've seen. So you shouldn't have to worry about it. If you're given the option, then choose the one that makes sense. Great. Our last question here, D, how will the data table plot and rules calculating rebound height change if the ball drops from only 15 feet? Essentially, which value changes? Is our start value changing, or is our rate of change changing? Okay. If we're changing the drop height, that only affects our start value, right? The rate of change will stay the same as it was, right? And the graph will slightly adjust, right? Because we're starting with 15 instead of 30, but it's still going to decrease at the same rate, so to say. Okay. So, any questions on this example? All right. So, last thing we'll do here is we're going to look at our discussion board. All right, so this discussion board, we have a very, very similar type of problem. We're using a softball instead of a tennis ball. Brand new softball should rebound to about 2/5 the height from which it was dropped. So the softball was dropped 25 feet from a window onto concrete. You're going to complete the table, write a now next rule, and write a symbolic rule, the same way that we just did with the example. Except we're not going to make a graph. I don't want you guys to have to draw a graph. Once again, you should be able to copy the table here. See if it works. And paste. Comes in a little small, but it'll work. I think we'll have to yeah, there we go. If you add an extra row, it'll fill in that missing box, and you can just type in your responses right here. So that's the easiest way to get this table in, is just copy and paste it from the question into your text entry, right? And then write the now next rule and the symbolic rule. So again, the important thing is you need to identify which is your start value, which is your rate of change. Use those accordingly.